Okay, I'm going to take a little bit here and go through, the background, at least my perspective on what you should take away in this course about data normalization and some related topics. It's a deep, deep subject mathematically, kind of built on set theory, and it's a beautiful kind of thing. And if it was a deep computer science oriented course we were in, then we would take a deeper look and embrace the mathematics and proofs and that kind of thing. But that's really not our take. And if we were designing and implementing large databases and that kind of thing was more of a DB programming and administration course, then we would get into some of the more subtle topics. But we are a data management course, so it's a kind of an appreciation and understanding and maybe a familiarization with some of the useful levels that go on with this. So take what you read in the chapters with a little grain of salt, look at examples, maybe for your guidelines. Am I getting what I'm supposed to get? Look to the assignments and what I have you do and the questions that we do. And if you have questions about that, then bring them on back. But we're going to start this with yet another DB example. You could start with just theory. Down here, this is from a Wikipedia, and you could just start defining things and proving theorems without having a picture of what the heck are they talking about. And this is a beautiful statement, and the whole theory by Codd and Date too helped. But Codd is E.F. Codd, Edgar or something. It was a big originator of ideas about these relational database management systems, what we've been dealing with, and the SQL language that's used primarily to attack them. There's also a relational calculus and a relational algebra, ways to format creating new relations, new tables from old, like a select statement. But SQL has been our take, and it's more applied, and it gets things done. It's how we get new results from what's already there. So pardon me while we wrap our mind around for a little bit an example, because it helps to illustrate some of what's going on in this idea. So our client is, or our application is, Accelerated Reader. I don't know if you have middle school or elementary school kids, but the idea is that students in a grade or a course, but they're in a particular grade, choose books to read. Okay, and presumably they read them, and they take a test on the book, and they score some points. And then they earn accelerated reader points based on, at least in this particular model, the book points. And the book points are related to the book. More complicated book, there's more book points, kind of like a harder dive at the Olympics or something. The test points is what they scored out of 100. And the way you figure out the AR points in this example is you take this times this over 100 times this AR factor. And the AR factor reflects the idea that a third grader only gets 85% of the credit that, say, a first grader would be getting to be doing the same thing. So, first grader doing all this, they get 100% of the value. A third grader gets a few less points. But the idea in Accelerated Reader is the points can be exchanged for prizes and trips and that kind of thing. And I think it's fairly self-explanatory what's going on, at least for the sample data. In here, that Tim, who's in the third grade, Red Bunny's Adventure, which is worth 100, scored 85. And if you do the arithmetic, 85 times 100 times 85, it's 72.3 points that he earned for that. And Tammy earned 81 points for not doing very well, but it was Paradise Lost. And so got more points for that, also being in the second grade, where it's only a 90% factor. So stop the video and look at this for a while if that isn't pretty clear and easy to see what's happening. Okay, so that's the application. It's important to maybe have an understanding. We'll see on the next slide a more practical version, the idea of a relation. It's really a table for us, okay? And this doesn't obey some of the ideas that we'd want from a relation. Well, technically it does, but it's got some repeated fields that are bad, but we'll get to that. But in database theory, a relation is a set of tuples. So when they say tuple and it's in the book, they really mean a row in a table. And you could get subtle little hair splitting. Well, we really, but that for us is really what it is. Um, and where each element, okay, and they're just giving the elements, names, D1, D2, all the way through DN, and a particular element is an attribute for us. Um, and this attribute is a member of a data domain. They're using capital D. They're really just saying that attribute has a type. Okay, so one way to think about, and a theoretical basis for thinking about what's going on when we have a table, is to think of a set of, when we say tuples, you maybe remember ordered pairs like x coordinate, y coordinate from um, algebra and geometry, analytic geometry, and maybe XYZ or X1, X2, X3. And that's the idea here. We can think of this is coordinate 1, the name, coordinate 2 is the grade, coordinate 3 is the AR factor, and we could deal with it like that. Much easier for purposes of human acting with it, though, is to, okay, we've got names that we can use, and that is much easier to see what's going on. So, when they talk about a relation, they're really talking about something that looks like this. And the relation is talking about the whole thing, especially the metadata. My wife was reading about Meta. Well, this was the Facebook company. Well, Meta is now the over-owning company for Facebook and some other things. And asked what meta means. And you might think of it this way. Meta X means X about X. Okay, so metadata is data about data. And there is data information. What's the entity name, and what attributes or columns does it have, and what are the domains, the types for the columns? All that's information or data. It's not data like this 1000 or that 72, but it's higher level. It's information about the information. So if it ever comes up, metadata is what we're dealing with when we kind of think of it this way, the structure. And a lot of the things like the normal forms we're going to talk about and relation really have to do with the structure and not the data. I show the data. To me, it helps get the aha of either why we do things or what's going on. But really, all of this is about how this thing is structured and set up. Okay, so we have this background example. Um, there are requirements for something to be even just a data relation, not a relationship like the foreign key, primary key thing. That's important to relational databases too. But a relation is just a well-formed list or a table. Okay, and that's really all it is. There are some requirements. A relation needs a name. Kind of think about the table. For the entity or a table or a list. If you think about all the tables in a database, they need different names. So when we go to try to pull things from one, we know which one it is. If two tables have the same name, and then select star from that table name, it's going to be ambiguous, right? So nothing too dramatic there. Tables have a name. They have a sequence of columns or attributes. Okay, both of these are kind of obeying that with unique column names. And actually, this discipline is forced on you even in Excel. If you're going to do pivot tables or try to identify something as a data table, it says we need column names, and you can't repeat. You can't have two columns with the same name. Kind of the same reason. It would be ambiguous to select first name from some columns, and you got three first name columns. Well, which one do you get? So nothing too dramatic there. The list has this heading row with names in it, and you can't repeat the names. No row, a tuple, record, instance can be a duplicate. So one of the rules to be a relation is this idea of non-duplication. We'll see the practical way to implement that is to have an identifier or primary key, right? If a identifier or a primary key uniquely identifies a record, there's only one record with that particular key, and you'll never have a repeat. This idea of accidentally repeating rows, double entry is a big issue in practical database use and building transaction systems. We may go there in a little bit, but that's really not our take here. It's more of a database programming thing rather than the data management. And each cell, I'm calling it, making up a term from Excel and using spreadsheets and that kind of thing, must contain a single atomic value. Okay, and that's where this fails to really be a relation because we've got three book points here and 2 book points there. any field, any kind of cell here that you're going to have to parse out, um, you know, take information from just doesn't fit as a relation. And that's why, in a database is having name with the first name space last name as the name in a field a good thing. If you never need the first name separated from the last name in the application, great. Then you just have that name. Okay. If you want sometimes the last name separate from the first name, then the relation needs to have it separated out. So, this idea of atomic, a specific, maybe depends on the application. But here we just have an awkward, um, it's a multi-valued field. How would I find the second book programmatically? It would be hard. I guess you could put commas or semicolons, something like that between. This one, so this one is not a relation because of that atomicity, assuming we want to get these specific values, which I think we would. This one actually happens to be a relation. It's got a bad thing in this repeated field, right? There, the most tests a student has taken is 3. So maybe one way to lay out the data is, instead of just like this, because of that atomic thing we don't want to violate, maybe we think about doing it like this. We put first test, and the results of the second test, and the results of the third. Well, that just leads to a bunch of confusion too. Tara just took one test, so I guess it's blank. What if Tim Smith takes another test? Do we add more columns? You don't like adding columns to relations. So this is technically a relation, but it's not a good relation. We can improve on it. We'll see an improvement on the next one. This one doesn't happen to be a relation, even though for picture purposes, it's easier to understand. Oh, and another thing maybe I didn't emphasize, that was going off on the atomic, but for a relation, everything in the column needs to be the same type. So if this is an integer or some, a fractional number, then it's that all the way down. If this is a string, it's a string all the way down. You don't have it string and then a date, then the word total, and then, kind of sometimes in an Excel spreadsheet, you'll lay it out and you'll kind of mix and match things just to make a spreadsheet presentation, and that's fine. That doesn't mean it's a relation. It's got to be the same things all the way down, perhaps with some being null, right? So null, sometimes we don't allow them, but sometimes they could be allowed. So this is in fact a relation. I have a link to where I got it's common, but they just said it plainly in the best. That's what it means to be a relation. So I said that this was a relation, but it wasn't a good version. So our first idea of kind of formalize, making the data better for storage, better for maintaining, inserting records, deleting records, updating, retrieving all kinds of things, and turning it into a database. That kind of refinement process is called normal forms, and they are applied one after the other. First normal form is less refined than second, then third, and on up it goes. And so this is our example relation in first normal form, 1NF. It's got a name, so it's AR test. So first normal form is a relation with no repeating fields. So they got rid of the repeating fields, and the way they did it was sort of, quote, the natural way, right? If I asked you to build a spreadsheet with that data, you probably come up with something very close to this. So we repeat Tim Smith 3 times, but it's different things going on here. And that kind of makes sense. So no repeating fields, and we've introduced a primary key. Tim Smith is student 101, and Bunny's Adventures is book 1001. And I've underlined this. The AR test has it's called a composite primary key. We'll talk a little bit about that. The combination of these two columns defines a unique record. One of the assumptions I didn't state is a student tests on a book one and only one time, or at most one time. They might not test on some of the books, but they can't test twice or 3 times on the book, or we keep the best record, best points, or we have one value for a combination of a student and a book. It'd be an entirely different thing. Like in D2L, sometimes you can have, take a quiz 3 times and take the average grade, take the best grade, take the worst grade. But that's our primary key. So realize these normal forms first and the others are really conceptual steps in DB design. That is, we wouldn't really then, okay, let's go out and create this database and populate it with data and then refine it better to a second normal form. It's a conceptual idea to help you make a better data model. And then when you get a good data model, that's what you implement. So it's really an idea kind of thing. I do put it out trying to help see, okay, those are some of the ideas that go into it. If you have a fully relational database, and we'll see this kind of on our last slide, it can be with queries and joins denormalized into one NF or something similar, but for analysis. For analysis, this is great. If you know familiar with pivot tables in Excel, you could slice and dice this in tons of ways, or other data business intelligence tools, and we will look at it in a little bit in this course using those tools. We could slice and dice all day and get lots of information out of this. And so the idea is you don't store it this way, but the tools of a database management system let you extract it this way, maybe to give it users and that kind of thing. So the way to go, and think about first normal form is, well, first normal form is a well-structured list. Has those nice properties of unique columns, data type all the way down, unique entries. They don't repeat. No 2 rows are the same. But this is not a good way to store information. It has, and in the literature, they will talk about anomalies, bad things, awkward things that can happen. Just some insert anomalies. Well, what about a student who hasn't taken a test yet? You could say, well, just put them in and have blanks all the way across. Okay, processing that is a little hard. Do you include that student or not? Same thing with the book. You could add a book here, but never had a test till somebody tests on it. Awkward, an anomaly. You'd like to avoid it. There's some delete anomalies. We kind of, if Tammy leaves the school, well, what do we do? Or the class, you might just say, well, get rid of, Tammy's records. She's not here anymore. Well, great. That takes this out. But associated with Tammy, kind of hidden, is the fact that the second grade gets a 90% factor. If Tammy's records go, that fact is lost. Ooh, bad. Okay, so, and I guess Paradise Lost she's the only one who's read it, so we lose the fact that Paradise Lost is worth 1,000 points when somebody else reads it. So this is not a good way to store the data for management moving forward. Second or third normal form will be better. I'm just pointing out when somebody says, well, what's an anomaly? They're talking about this kind of thing. Update, if later on we say, Bunny's Adventure was a little harder than we thought, and it should be worth 150 book points. Well, we got 3 places to update that up, and then we've got to go update all the AR points to go with it. So if you're thinking ahead, this is really kind of a formula, cha-ching, and so that's one thing we're going to get rid of. That is, we don't need to store it. If it's a formula, we'll calculate it when we want it. And there's really 3 or maybe 4 things going on here, and we've only got one entity. We've got students, we've got books, we've got tests, and if you're really thinking of it, we've got grade factors. So don't be surprised if that makes a little sense now that we end up with 4 tables, 4 entities in our data model rather than this, even though this is a great list to analyze from. So first normal form looks like something you would do in Excel. All right, and that's going to take a digression on keys, because keys are the important defining aspect or analysis aspect for kind of doing this normal forms in a good data model. And I apologize for a slide that's like a page out of a textbook, but we needed the words just because it goes. That's the way it goes. When we talk about a key in this case, a key in general, a lot of times when people say, oh, the key is, they mean the primary key or identifier, and that's the usual use. The key to this entity is blah. Okay, but a key in general is a subset of the relation's attributes. Okay, so we got this list of attributes. And the specification values for the key defines a subset of the rows of the table. What the hell is he talking about? We've been doing this all term. If we sort of say select, from this entity here where section is A and instructor is York, okay, that determines 2 rows. Section A here, I could highlight, I got ahead of myself, want to, what's one of these? Yeah, section A and York, section A and York. Okay, so one way to think about a select is that, what we've done is identify values for a particular key, which is a combination of columns. Okay, and so that's a key is really just sort of the subset of the attributes, and when we give values, it determines a selection from a smaller table made up of rows that fit the key. The empty key, specifying nothing, returns everything, right? So kind of select without a where clause would be the way to think about that. It's not going to come up important for us, but in general, there are 2 to the n potential keys for a table. We have 5 columns. It turns out there are 32 keys. Nothing, right? The null key, each of these individually, each of these in pairs, each of these in triples, and each of the any fours you can get. So it's there's lots of potential keys. Usually it's 1 or 2, or we don't even think about when we did say like a select statement and said section equal A and instructor equal York. We weren't thinking we were providing a key and a value, but technically we were. All right, a super key defines a unique record, right? That is, it's a specification of values for something where there's only one. We're guaranteed there's only one record. It's not so much that there's, only one record in the data that I'm looking at. There will only ever be one record in all the data that could possibly be in there. And so, I guess there's one record with section B and Schultz. That's not what we're talking about. Schultz could teach another section B, easily conceivable. But a super key determines a unique record, but so does what's called a candidate key, or what we're familiar with a little bit, a primary key. If you get down to it, a super key, though, may have attributes that aren't required for uniqueness. For instance, CRN and instructor together are a super key. CRN is course resource number. It's a unique number just defined to every row. It's a super key because it defines one record, determines what record, but we don't need instructor. So think of a super key that may have superfluous columns if what your goal is to uniquely define a record. Okay, a candidate key is kind of a minimal super key. All right, all the key attributes are required for uniqueness. So an example is course and section. It does turn out that course and section uniquely identify a row. Great, tell me the course and section. You can tell me the instructor and how many can maximally enroll and like that. But it's if you lose one of those columns, it doesn't any longer define a unique row. So candidate key, think of it, it's a candidate to be the primary key. That's kind of why they call that. But a candidate key defines a unique record when you supply values. And a primary key is one particular candidate key chosen as the main identifier for the table. So, and which of candidate keys should you choose is a good data modeling question in general. Like a lot of database stuff, though, it depends, right? You tell me the situation, I can help guide, but it's a primary key is going to be one of the candidate keys. A multi-key is something that will, in general, return more than one record, right? Section, if you ask for all those that had section equal to B, you get this guy and this guy, you get 3 records as a result. Okay, so section is a multi-key. I guess multi-keys are all those that aren't super keys, candidate keys, or primary keys. But a primary key is a candidate key, and a candidate key is a super key, right? But it doesn't go the other way. Good. So, but we have a primary key that defines uniqueness is what we ought to take away. A composite key has more than one attribute. So course section is a composite key. But max and roll, just one column is not, right? A surrogate key is when a value is made up. Okay, typically it's an integer, often it's an identity. A value is made up to has no relation to the data, but to guarantee uniqueness. The made up value is guaranteed to not repeat ever, and so it will give you a primary key or a candidate for a primary key, a candidate key. But it's called surrogate because it's really not out of the data. And that's really actually what makes them good for primary keys. They have no relation to the data, and so there's some benefits to that if you're going to build a database. But for now, just realizing that's when it just makes up a number or something. Usually it's a number. And a foreign key we're familiar with is when an attribute in another table, like maybe a student's schedule, refers to the CRN here to find out that it's York teaching it and there's a max and roll of 30, right? But that's the attribute in the other table that refers to a primary key in a main table. All right, so that is a little digression on keys. You remember where we were. We had this first normal form, okay, and it was nice. And let's talk about this refinement to thinking about, well, how do I refine something and ensure that it's in second normal form? Second normal form has to do with columns that depend on just part of the key, functionally dependent on, or called transitive dependency. That is, so first normal form, if it doesn't have a composite key, you're already in second normal form. If there's only one column in the key, then you can't depend on part of the column because there's only one, and it's then assumed that everything in the row depends on that. But we don't have a single key. We have a composite key, and there are some columns that depend on just part of the key. The student's name, the grade, and the AR factor. Well, all I really need to know for that is the student ID. Okay, and when the student ID is the same, those three things are the same. So the idea is, just conceptually, you say, oh, I really have this entity that I called student, and let's pull the information that's just related directly to the student into that entity, right? And then pull it out, and I don't need to keep a track of that for every test. I just need to have this foreign key relationship that points back. Similar thing is, well, what about book ID by itself? The book title, the book points depend on just the book. So take book ID, make another table, and book title, book points, and that's another entity then. And with a primary key that's just got a single entity, and it has just book information. And then what remains, still calling it AR test, can be collapsed a little because we don't need to carry on all that baggage. We can use primary foreign key relationships in the database to get the information. And so, what was the book and book points for this one? 1004 was Paradise Lost and 1000. And who was the student who did this one? 103 is Tara. So one AR test may, I got this backwards. I got that backwards. Yeah. This one's backwards. This one's okay. So it's N1. An AR test can refer to one book. An AR test refers to one student. One student can do many tests, and one book could be part of many tests. So please take that. I'll correct it before I give you the copy. All right. So and this addresses several of those anomalies we talked about. If we get a new student in, well, we just add the student record. It might not have any tests yet, so nothing to join to, no problem. Same thing with a book. We add the book and like that. We can't delete books maybe that have been tested on or students that have been tested, but the database can guarantee that. If we need to change Bunny's Adventure to 150, well, we change it in one place, and that's good. One fact, one place. There's still some issues, deletion and update anomalies with grade, an AR factor, and AR points. Okay, this one, we don't need to store because we can figure it out. And factor, if you're kind of thinking of it, doesn't really depend on the student. It depends on the grade, which depends on the student. So that's kind of a transitive. This depends on this, depends on this. And that's what third normal form will help us to clear up. So we still got a little bit to do coming around the corner here. I know that looks bizarre, but any 2NF attributes, that second normal form, that are functionally dependent on other non-key attributes, right? So the AR factor depends on grade, which is a non-key attribute. AR points depends on test points, book points, and AR factor, which aren't key attributes. So that's what that's saying. Should be moved to their own table, and we can see that here. And I got this wrong, but let me get that done. Right, moved to their own table or removed, like I did with AR points here, because we can calculate it when we need it, right? And so this then is that data in third normal form. Now looking at it, it doesn't give you that impact that first normal form is that, oh, I can see what's going on here. But for the model to store the data and support transactions and take updates and deletes and do them efficiently, and then when you need it, produce that denormalized form, this is the way you should set up that database. All right, so this is third normal form. Non-key attributes depend on the key itself, right? So the factor depends on grade, not before in students. Okay, there are other levels of refinement. The book talks about them. Boyce-Codd normal form, fourth, fifth, sixth normal forms. But this third normal form, I call it the sweet spot for data modeling. I've rarely run into a real situation where you needed to worry too much about some of these other issues. It does happen, and when you get there, you probably have some experts to help anyway. Where these more refined instances turn up is when there are kind of several candidate keys, and maybe they are each determining some different things, and that's when that extra refinement goes on. But for an introductory course, I would stick with, and it's hard to kind of find illustrative examples that just let you see it. Think about here just to demonstrate clearly a third normal form situation. It wasn't impossible, but you really had to kind of think about it a little bit and follow along. All right, so there's one short way then to put all this is a relation's attributes will depend on the key, meaning primary key, the whole key, and nothing but the key, so help me God, right? Kind of like the swearing statement at court, if that's really there. So help me God. God, remember, was the early thinker on this, and that's what we want to have happen. We had the attributes in student depend on the student ID and nothing else. That wasn't the case before. The test points, I need to know the student in the book to be able to produce test points. So it depends on the entire key, the whole key, and nothing but the key. Back in, when AR factor was dependent on grade, dependent on students, we had something that did not depend on the key, and that's not good form. All right. So, that's the talk. Hope it helps. I'll be in touch later.